Hola, ¿qué tal a todos? ¿Cómo están? Solamente vamos a esperar unos momentos antes de iniciar, así que estamos iniciando en aproximadamente 1 minuto. Así que por favor, esperen que ya empezamos pronto. Hola, ¿qué tal? ¿Cómo están todos? Hola, ¿qué tal? ¿Cómo están todos? Comunidad de AWS Perú. Una vez más, hoy sábado, estamos compartiendo un montón de información, un montón de cosas muy interesantes acerca de la nube de Amazon Web Services. Y pues hoy, así como está aquí ya con nosotros, les vengo a presentar a un AWS Serverless Hero que viene a compartir con nosotros algo sumamente especial, que es un stream realmente increíble acerca de pues, serverless en general y construir aplicaciones realmente robustas. Así que sin nada más vamos a darle la bienvenida y vamos a hacer el switch en inglés para comenzar a conversar con Gunnar Grosch. Hi Gunnar, what's up? How are you doing?
Hey, I'm good, thanks. How are you?
Yeah. Well, thanks first of all of being here just in our user group and welcome you to Peru. Hopefully, well, I will be in my mind comes that every time I invite someone out of Peru, I would like to invite here to come and visit Peru, but maybe 2020 is not the year exactly to do that. But we can share virtually and share information and share your knowledge with Latin America and with Peruvians. A lot of serverless applications that you're going to talk about here. So first of all, tell us what you do, what we're doing, where you work, and actually about the talk that you're going to be giving right now about building reliable serverless applications. So please, this audience is all yours, Gunnar.
Yes, well, thank you very much. Thanks for having me. And as you say, it's I want to come to Peru and do a talk there, of course, but well, a virtual one works for now.
Okay.
It's 10 p.m. in Sweden right now, so approaching quite a late night. I have a long session for you as well, so hopefully it'll keep you busy for about 2 hours. We're gonna talk about building reliable serverless applications. and look at some patterns and practices, look at what reliability is. And we're also going to look at a practice that's called chaos engineering to see how we can use chaos engineering to better make our applications better, to make it easy. So that's more or less the outline of the talk. And if you have any questions during the way, just put them in the chat, and I'll try to remember to switch back and forth and look at the questions as well. Otherwise, of course, we'll take the final questions in the end as well.
Yeah. Give me a minute about that. I want to switch to Spanish. Muchachos, para todos los que estamos oyendo, vamos a sortear varios créditos de $25 de AWS, así que estén atentos porque a Gunnar le dije que hagamos preguntas durante el stream, o pueden tomar las preguntas y llevarlas al final del stream, generar un poco de expectativa, un poco de interés, discusión, y ustedes también serán premiados por la participación y continua durante el stream. So, don't forget, Gunnar, to ask the questions I told you during the stream or at the end of the stream, whatever you feel more comfortable with.
Yep.
So, go on, please.
All right, so let's jump into it then. I have quite a lot of slides with a lot of information, and let's just get started and see how far we come. All right, so the topic, as I said, is about building reliable serverless applications. And this is the agenda that we're going to go through. We'll start off by looking at what serverless is. A lot of you, if not all, probably know already what serverless is, but it's always good to have this as a baseline so that we know what we're talking about. Then we'll move over to looking at reliability. What is reliability, and some other of the R's in regards to building reliable applications. Then we look at the building part, and that is the practices, the patterns that we're using when building serverless applications, and things to think about to make them more reliable. Then we move over to chaos engineering, see what chaos engineering is, how we're using it, and then look at how we can use that to improve our serverless applications. And in the end, I'm gonna show you some demos of how we can put this to practice as well. So already mentioned a few things about myself, but I work in Sweden at a company called Opsio as an evangelist there. We work in the Nordics mainly. My background in tech is quite long. I'm turning 40 next year, and I've been in tech since I guess I was 19, 20, so about 20 years. In Sweden and in the Nordics, I am an organizer of both AWS user groups, serverless meetups, different conferences around serverless and AWS as well, including serverless days in Sweden and serverless days virtual, which is a global virtual event that we're doing as well on a quarterly basis. I have been named an AWS Serverless Hero, which is a great honor for me, a title that AWS, I guess they give us for doing things around serverless and around AWS and being spokespersons for serverless. And once again, it's a great honor to have this recognition from AWS. And lastly, but perhaps most important, I'm a father. I have 3 kids. And I jokingly say sometimes that they are what brought me into the chaos engineering field, because having 3 kids, that's a lot of chaos. All right, so let's jump into it. Building reliable serverless applications. We'll start off with the serverless part of it. So this is the AWS definition of serverless, and it states that serverless allows you to build and run applications and services without thinking about servers. And The without thinking about servers part is perhaps the most important one. And this is not so much about the actual servers as it is about what running servers means. It's about letting someone else do the long time work that is involved with running servers. So it lets you focus on maximum business value instead. And it's not only about functions as a service like AWS Lambda, but the serverless landscape today consists of a lot of different services, and more services are moving towards serverless and fully managed. So we usually say then that there is no server management in serverless. So there's no need for us to provision or maintain any servers. There is no software for us to install or runtimes to maintain and administer. And also with serverless, we have what we say is flexible scaling, that the applications that we build can be scaled automatically from 0 and to the highest peaks, or simply by adjusting the capacity units of the service rather than the number of individual servers, like with more traditional infrastructure. And with serverless, we also pay for value. And pay for value means that we pay for a consistent throughput, or perhaps the execution duration of a service, rather than, once again, the number of actual servers. And also with serverless, it provides built-in availability and fault tolerance. So you don't have to architect for these capabilities on the service level, since the services running the application provide those by default. But it's important to remember that this built-in availability and fault tolerance is at the service level. You still have to do the architecting to get it to be high available on an application level. So if you've ever talked about serverless with an old server hugger, you probably heard this phrase that there are still servers in serverless, and that's true. There are servers, but we just don't manage those. So serverless in itself, it is, or rather, serverless. We like to say that serverless is distributed by default. So it is a distributed system that has multiple components, and they are located around in different services, different machines, and then coordinate together to appear as a single coherent system. And that is the definition of a distributed system. So with serverless, we have that as a default. Serverless applications are distributed by default. And building distributed systems, that usually means that we have a higher level of complexity. Sure, it is easy to build using serverless. We can easily get started. We can easily build quite complex applications. But having them being distributed means that we are adding complexity, which sometimes makes it harder to get a complete overview of the entire application. All right, so with serverless then, some of the pros with serverless are also sometimes cons, meaning that since we don't have any servers to manage, it also means that we have some possible failure modes, things that can go wrong that we can't control. We don't have control of the underlying infrastructure. And we often talk about heavy lifting when talking about infrastructure. And with serverless, we have less heavy lifting since we don't manage the infrastructure. But we have to remember that every time someone builds a system, builds or set up infrastructure, they usually learn a lot about how that infrastructure works, how are the possible failure modes, how can things go wrong. You usually learn that when setting up a system or setting up infrastructure. With serverless, once again, we don't have that. Things are unknown for us. And as I mentioned before, it's not only about AWS Lambda. There are a ton of different services to choose from today. It can be DynamoDB, SQS, SNS, different serverless services or fully managed services. And each of these different services, they have their own failure modes, things that can go wrong in those services. And piecing together these servers, different services, brings even more failure modes to us that we are exposed to. And for every service and for every function, every Lambda function that we use, we have a per service and per function configuration. So for each of them, we have configuration. We also have security policies that is individual. And having a lot of different configuration and security policies, that's also a way that we might introduce failure into our applications. So we have to be even more perhaps thorough when we're doing configuration and setting up security policies, since we do that on a per function and per service level. And building serverless applications mean that we have architectures that are more granular. That means that they contain more different small parts. And thinking about how we build a serverless application, we usually do that with Lambda as one of the most common parts. And for each function, or for each function within our application, we have a separate Lambda function. And then we have all of the other different services. So they are more granular in that way. And we like to say also that chaos is inherent in serverless applications. And with chaos in this case, talking about the things that can go wrong. And this is where the word chaos in chaos engineering comes from, but more on that later. But all in all, more inherent chaos in the serverless application. And this is not to scare you about serverless, because serverless is great. I'm all for serverless. We just have to be awake to that this can be quite complex sometimes. All right. So let's look at some of the different services. I'm not going to go through the services in detail, but just a brief overview of them. Starting out with then AWS Lambda. And Lambda is a serverless event-driven code execution service. And that means that we have a certain amount of code that we are able to run in an event-driven fashion within the platform. So we set up one or many different Lambda functions and are then able to execute those. And today, AWS Lambda is able to handle a lot of different languages and runtimes, and you can even bring your own runtime using custom runtime API. Lambda in itself, it has built-in fault tolerance and scaling. It uses a quite simple resource model where you change the memory that is allocated to each Lambda function. And when you change the memory, it also then adjusts the amount of compute or CPU that you get, and also the network throughput. So more memory means more CPU and more network throughput. And Lambda, as I mentioned previously, it has a fine-grained security configuration. So you're able to set your policies for each Lambda function. And this is both for the invocation, that means who can run the Lambda function, and then the execution, what the Lambda function then is able to access. And with Lambda, you, of course, as with all everything that is serverless, you pay for use. So you pay for the actual duration and the memory that your Lambda function consumes. So if it runs for a certain amount of time, you're paying for that time. It doesn't cost you anything besides that. Another service that we use quite regularly is Amazon API Gateway, and that is a fully managed service to build APIs, and it's also APIs at scale, which means that this is a service that you can use for the smallest type projects up to very, very large services or applications, because it scales as you need it. And it has support today for both RESTful APIs, a REST API, and WebSocket APIs. And the RESTful API today consists of 2 different versions of API Gateway. The traditional one is the REST API, and then there's the new one that was released at reInvent 2019, which is called HTTP APIs. And the naming perhaps isn't great with that service, but searching for HTTP API on Google brings up quite a lot of other hits. But calling it a Amazon API Gateway HTTP API, so that's the new one. And you can integrate this with the Elastic Load Balancer and Cloud Map, for instance. You can use it to then have private integration towards things that you're using, even on-premise, using API Gateway behind a load balancer, for instance. You can set up throttling, so you can decide upon how much traffic it will allow in through the API. And you have great control over both authorization and usage of the API with built-in functionality. So API Gateway, a fully managed service for APIs. Moving on, another service that we use quite often with serverless is a fairly new service that's called Amazon Event Bridge. And Amazon Event Bridge is a fully managed and scalable event bus. What that means is it's a service that is used to you push events in and out of that service. And events today, that's something that is commonly used in what's called event-driven architectures. Event-driven architectures is compared to perhaps the one that was previously most used, the more action-driven architecture, where you have different actions happening. In this case, instead, we're talking about events, and an event might be that a user is created, is an event, an account is updated, and so on. So that's the event that happens that you're then able to use within your architecture. And besides the events that you have within your own application and the services that you use it with, you have integration, native integration with a bunch of different SaaS providers. This can be SaaS providers that have ticketing systems, monitoring systems, and so on. So you can take use of the events that is created in those systems and then use them within EventBridge and in your application. EventBridge today has over 100 built-in event sources and targets. And sources, that is different services where the events are created, where things happen, an event happens. And targets, that's where you're pushing your event afterwards. For instance, pushing it to a queue or pushing it to a notification or to a Lambda function, for instance. You're also able to use EventBridge with your own applications. So if you have an application that is completely or a separate application from other AWS services, you can use EventBridge, create events and push them into EventBridge as well. It also has a neat feature that's called Schema registry. And the schema is basically how your events look, the contents of your events. And a common, perhaps not issue, but a common thing that makes it harder to work with event is that different teams, different companies, they look at events in different ways. But having a shared schema registry where you're able to store how your events looks makes it a bit easier to work together between teams, for instance. You're also able to use something for discovery of events. So you can look at events that is pushed through the service and register them in the schema afterwards as well. So that's Amazon Event Bridge. Then we have Amazon Simple Notification Service, SNS. And that's, as the name suggests, it's a notification service that delivers messages. And it's a really durable system in that it can have a lot of messages being delivered, and you can trust the delivery of the messages as well. You have different retry policies, and you have the usage of dead letter queues as well. So if a message is unable to be delivered, you have the possibility to store those messages within a dead letter queue in another AWS service, that is. There are options for message filtering, so you're able to filter how messages are delivered. You can use encryption and different privacy settings as well, and even use SNS with mobile notifications. So SNS can deliver messages to mobile as well. So SNS is a service that is quite commonly used for messaging within your serverless applications. Then we have the Simple Queue service, SQS. And Simple Queue service is besides API Gateway and Lambda, perhaps one of the most common services that's used within serverless applications. So this is, once again, as the name suggests, a queuing service. So you're able to queue messages. And this has support for two different kind of queues. We can have what's called a standard queue. And a standard queue is a queue that messages are stored within the queue, and then you're polling that queue for a message, and you will just pick one of the messages. But you also have a different kind of queue that's called a FIFO queue, or a first in, first out queue. And the FIFO queues, they are delivered, as that name suggests, in the same order as they are delivered to the queue. So when you're building applications where the delivery order of messages are important, you have the option of using these FIFO queues instead. And that might, for instance, be talking about transactions, for instance. Perhaps it's important that how we do transactions from an account, for instance, the order of those transactions is important. Well, in that case, we should use a FIFO queue instead of a standard queue instead. And with SQS, of course, we're able to keep sensitive data secure with encryption as well. So let's look at, first, let me just see if there are any questions. No. All right, so let's look at the execution model for Lambda, an icon that should have been hidden, I guess. So this, when we're using AWS Lambda, we can invoke it in different ways. And this is a common way. We're using a synchronous execution of Lambda, a push execution. In this case, we have an Amazon API gateway. We're building an API web service. A user or a browser, a client, is then doing a request to a specific API gateway URL, and that invokes the Lambda function. So that's a synchronous call. And doing synchronous executions means that when the client calls the API gateway, the Lambda function performs its execution and its attended task, and then replies back through API gateway to the client. So the client waits for a response from API gateway and in turn then Lambda. That's a synchronous one. But we also have asynchronous execution. And asynchronous executions means that the client isn't waiting for a response from the execution of the Lambda function. Asynchronous ones, they are usually event-based. For instance, that the execution happens when a message is put in Amazon SNS, for instance, or an object is created in an Amazon S3 bucket. That in turn invokes a Lambda function that does something with the event or with the contents of the bucket, for instance. Let's say we're uploading an image to S3, which invokes a Lambda function, which then in turn perhaps transform the image in one way or another. So that's an asynchronous one. These different types of execution is something that we are able to use then within our architectures to make them more reliable. Then we have the stream-based execution. And a stream-based one, that is based on primarily DynamoDB and Amazon Kinesis. When an item is created or updated, for instance, or deleted, we can have Lambda being invoked based on that. So we're setting up a stream from maybe DynamoDB, and for everything that happens in that stream, new items, updates, deletes, and so on, we invoke a Lambda function that then uses that event to do something based on that update. The stream-based one, that can be used in many different ways, but it can be used, for instance, to do changes in another DynamoDB table. It can be used to use the data that is created and updated and then transform that data in a specific way. It can also be that we're streaming data through Kinesis and then use that data to store it somewhere else to transform the data, for instance. So that's the stream-based execution. And then we have the one that's already shown a bit, but that's the poll-based one. And that's based on Amazon SQS, the queue service. So when we put things within SQS and we are queuing a message, for instance, in SQS, we're then able to invoke Lambda based on that. And the last one with the poll-based, and that's definitely something that we use quite a lot to be able to build more reliable applications. Of course, we need to have the right fit for it when we're able to queue things. But with the help of that, we can create applications that are perhaps more scalable and more tolerant to issues. So these are the different execution models we have for AWS Lambda. So let's look then at how we can use these different services that I talked about to build something. So a simple serverless web service looks usually this way. So we have a client. The client in turn talks to Amazon API gateway. We have AWS Lambda behind the gateway. We have DynamoDB as a data store. So the client makes a request to API gateway. So this, as we said, was a synchronous invocation. So API gateway in turn invokes AWS Lambda. So we have to wait for Lambda to do its thing with the execution. And in this case, Lambda is reading or writing or updating data within DynamoDB. DynamoDB responds back to AWS Lambda with the data that is read, for instance, which in turn goes back to API gateway and then back to the client. So all of this traffic back and forth for a simple serverless web service. And this is in many cases the basis for a lot of things that we build using using serverless, and perhaps the most common thing to get started with as well. So then let's move over to the reliable part of building reliable serverless applications. We looked at how or what serverless is and how serverless works. So now let's move over to the more reliable part of it. Quickly, I need to restart my PowerPoint. Just a second. You can look at my demo site in the meantime. My other screen got blank, so it made it a bit hard to read along the way. I'll be right back with PowerPoint. Let's see. I think we have a question as well, so let's get that in the meantime. All right, so PowerPoint is back. Just going to get back to the right slide once again. And let's look at some questions. What is the difference between AWS Event Bridge and SQS? I would rather say that the services that are close together are Event Bridge and SNS, the notification service. They are usually the ones where people previously, in many cases, used SNS. They today use Event Bridge instead. So SQS is a queuing service, and Event Bridge in itself doesn't have any queues it can store events in. So usually you have Event Bridge and an event is passed to an SQS queue, for instance. So while Event Bridge is where events pass through, SQS is instead where we're storing messages in a queue instead. Another question was, can we use ALB in front of Lambda instead of API Gateway? What would be the main difference between them? Yes, we can use ALB in front of Lambda. The first difference is that using ALB means that we're moving from serverless, because ALB is instance-based. ALB is a service that we're paying by the hour. And so even though there's no traffic, we're going to pay for ALB. And by adding that, our application becomes server full instead of serverless. So that's one thing. The main difference otherwise is that a lot of the perhaps controls that you get with API Gateway when you're building APIs, you're configuring your API, you don't have that with ALB. So since ALB is a load balancer that's able to do some routing of traffic as well, API Gateway is mainly an API service, fully managed APIs. So sometimes we use API Gateway and you have ALB behind an API Gateway, so you're able to pass some traffic through to the ALB, which then perhaps goes to an instant-based service that you're running as well. There is a specific pattern that I don't have in this presentation. It's called the strangler pattern, which is perhaps not the best of names, but it is a pattern that is commonly used when you're migrating from an old server full service into a serverless application. So then with the help of API Gateway and with ALBs, you're able to move service by service from the old application, the old service, into the new serverless applications. So in that case, you're using both API Gateway and ALB until you've moved everything into serverless. All right. Let's move back to the presentation and we'll look at some more questions later on. Back to the reliable part of building reliable serverless applications. So reliability, this is the definition of reliability. Reliability is the probability that a product, system, or service will perform its intended function adequately for a specified period. And the perhaps most important part here about reliability is its intended function. So it's not a matter about everything within the application working. It just has to work with its intended function. Users are able to log in, you're able to buy things, add things to the cart, and so on. That's the important part of building reliability. And reliability, that's basically created by using different patterns and practices. The patterns that we use to get something to be more reliable, and the practices we use to keep our applications more reliable. And reliability is not the same as quality. We can have, looking at a car, for instance, we can have certain brands are branded as high quality cars, but they can still have issues. You can still have a car that breaks down, even though it's a BMW or a Mercedes-Benz that has high quality. So that's not a reliable car just because it has high quality. It has perhaps thicker doors and smells better. So reliability is not the same as quality. So besides reliability, there are some other words that we use quite commonly when we're referring to our application and how they work. Another word is robust or robustness. And robustness within a computer system is its ability to cope with errors during execution. That means that things go wrong within applications and within services and so on. But the way that they cope with those errors while executing, that is what's referred to as robustness, if they're able to cope with those. And a lot of the services that we have in AWS, the fully managed services and so on, they are robust. They're robust in the way that they are able to cope with these errors. And then we have the word resilient. Resilient is commonly used. A lot of people use it interchangeably with reliability, but a resilient system is able to adjust its function either prior to, during, or following different events. And by adjusting that function, it can sustain the required operations. Both when expected things happen and when unexpected things happen. And in regards to resilient, I know that a lot of my friends in this industry use resilient, talk about resilience and so on. But I think this is a great quote by Dr. David Woods. He's a well-known name within the resilience engineering and safety engineering fields. He says that resilient isn't something you have, it's something you do. It means that a system in itself, the technical parts, isn't resilient. It's rather the people running the system or building the systems that use resilience when they build the system or when they run that system. All right, so that's the perhaps dictionary definitions and looks at reliability and robustness and resilience. So let's move over to some of those patterns and practices that I mentioned before. And that's the building part. And this is perhaps the fun part as well. And a lot of this is opinions, and my opinions in many ways. And you might disagree with parts of this, and that's fine. That's, I guess, what opinions are. We can have different opinions. And for me, this is one of the greatest motivations behind why we want to work with reliability and why we want to make sure that our applications are reliable. So we shouldn't ask what happens if a system fails. We should ask what happens when it fails, because all systems fail sooner or later. It's a matter of when. All right, so the first part, one thing that we try to do as often as possible when we're building our applications is to decouple architectures. So a decoupled architecture, or rather a loosely coupled system, that's one where each of its components has or makes use of little or no knowledge of the other separate components. That means that we break down the system to different parts that all can work by itself. And so they don't really care about what the other part of the system is. So let's look at an example of how we can decouple an architecture. So client, once again, in this case, storing an object in S3. And that means when we're storing something, the client gets a reply back or a response that says that the item has been stored. That creates an event that is sent to SNS. And using SNS, that event or that message in SNS, we're able to decouple from S3 in the way that we can, for instance, send this message to a queue, SQS. We can invoke a certain Lambda function, that, for instance, takes whatever object we stored in S3 and do something with that. We can have a separate Lambda function that perhaps creates a notification within a ticketing system or something like that. So that's a simple example of how we're working with decoupling. So instead of having the Lambda functions directly interact with the event that is created from S3, we decouple it using SNS as a message broker in this case. And the event that we're storing in SQS in this case, well, we can then either have that stored there, use that as more or less a dead letter queue, or we can use that to perhaps decouple the application even further downstream within the application. Let's look at another example. So we have a SaaS provider of some sort that has an event. Let's say that it is a ticketing system. A ticket is created within that SaaS application. So that event is then passed into Amazon Event Bridge. From Amazon Event Bridge, we're then able to fan out this message and send it to, once again, we can push it to SQS and store the object within a queue and queue it. That means that even though something might happen, we are able to queue that message and store it within the queue. We can invoke a Lambda function from the event in EventBridge, have Lambda as an event destination, and we can invoke a state machine within AWS step functions, for instance. And further down, after the Lambda, for instance, we can use DynamoDB and change data there and so on. And with the SQS queue, well, we can do whatever we want with the message that we store there in the same way as we saw in the previous one. So this is another example of how we use an AWS fully managed service to decouple our applications. In this case, by taking the event and passing it through EventBridge, where we're able to then filter and send the event to the destinations that we choose. Next up, we have the matter of error handling, errors and retries. And when we build applications, most of us, if we do development, we're used to handling errors and retries within our code. That's usually how we do it. But with AWS and AWS Serverless services, we have a lot of functionality to handle errors and retries within those services. And it is really good practice to use those as much as possible. So instead of writing those error handling and retries within our code, we can leave it up to the service instead to do that. They are usually and quite certainly better at handling retries and errors than we are. And these errors then might be exceptions, timeouts, out of memory, throttling errors, and so on. And these are errors that instead of us handling those, we leave it up to the service to do it. An example of that is, for instance, that we have a service where something is passed in through Amazon Kinesis, which invokes Lambda functions and then stores that data in S3. But if there is an issue with S3, it might happen, it has happened before. And S3 in this case is an example. It might be whatever service downstream. If there is an issue there, well, we should fail up the stack. We shouldn't catch the error using try catch as we're perhaps used to. So instead, we should fail the function and let AWS handle that error and retry. So we can return the error instead to the invoking service. And within the services, we usually have retry functionality, so we can configure that, the built-in retry functionality, so we can reprocess these events. We can also use, in all places where that's possible, use dead letter queues. So we can pass the event to a dead letter queue, the failed event, and capture it there. And when we use a dead letter queue, which basically is an SQS queue, we can then build our retry functionality around that, or a reprocessing functionality. So we, for instance, if in this case we have an event that's failing, we're pushing that to DLQ, and from the DLQ we can watch the message, see what happened with it, and then we can try to replay it again to store it correctly the next time. So let AWS handle errors for you. This is a basic one, but one that is, I think it's important to really think about. When we're building using AWS Lambda, try to use as little code as possible. Less code, more functions. We want to reach this stage usually where we have what we call lean functions. That is, functions that has single purpose. They usually give us the possibility to have total failures within the function. Thinking about having a large code base within a Lambda function where we have lots of if this, then that, and so on. If there is a lot of functionality within the same function, well, it's harder for us to leave the error handling and retries over to AWS. So instead, try to break down your functions to as many functions as possible instead, so that you have single purpose functions. And by doing that, well, then we can pass the failure back to the invoking service, the service that invoked the Lambda function instead. And that's better. Checking for questions. Let's see. Even if we don't use Lambda, are Kinesis and Dynamo considered serverless AWS services? Yes, definitely. A common pattern that we're seeing today is that or that's actually good practice to not use Lambda functions if you don't have to. And so the Kinesis and DynamoDB, for instance, they are definitely serverless services, even though we don't use Lambda. But instead, if we're able to not use Lambdas, that's good practice today. Lambdas should be used to transform data, not transport data. That's perhaps the guiding principle when creating our architectures. Are the serverless components of the decoupled architecture similar or the same as microservice architecture? Well, it depends is perhaps the answer. Serverless isn't equal. Serverless services isn't equal to microservices, but it definitely has a lot of the same principles behind them. The way that we try to break our applications down to smaller parts, but a microservice can still be quite a bit larger than a single purpose service within a decoupled serverless application. So they might be smaller than your traditional microservice architecture, but they are definitely quite similar still. All right. Moving back, I'll get back to some more questions as we go along. Retries within serverless. And retries are definitely a vital part of distributed systems. When we're building a distributed system, we usually must have retries. And every time we don't have to build a retry logic, that is good. If you ever try to build retries yourself, it can be quite complex, depending on the system, of course, but doing it correctly is quite complex. But there are a few things to keep in mind regarding retries. For instance, that the same event can be delivered more than once within your application. And for that reason, we often talk about what's called idempotent operations. Idempotent operations. It means that it is an operation that can be repeated multiple times and always provide the same result. For instance, an operation that sets a user account to active, that is an idempotent operation, because every time we run the same operation, it should just set the user to active. It shouldn't switch it back and forth. An operation that checks for a specific record in a database and then creates it if it doesn't exist. Well, since it's first checking if the record exists, it doesn't create it twice, because the second time it will check and see that it's already there. So no matter if we run these operations multiple times, it should still be the same result. But instead, think of the operation of adding $10 to a bank account. Well, if that operation is done twice, it means that the user will receive $20 instead. So that's not an idempotent operation. So that must be handled differently. So using retries, using the built-in retries is good, but think about how does your functionality, what does your operations do, and what happens if they are run more than once. Looking at retries then, some invoking services, they retry themselves. For instance, Cognito and Alexa. Others do not, but they can return errors to the client. So a synchronous Lambda, they return failures to the invoker for retry. So for instance, a client invokes a Lambda function through an API gateway. Well, if there is an error, that is returned to the client. So your, for instance, web browser would receive a 400 or a 502 or whatever the error is. And then it's up to the client to press refresh, press that button once again, and so on. Or if the front end handles that for you. And so that's synchronous Lambdas. And asynchronous Lambdas, they will retry up to 2 times and 6 hours. So if you have an asynchronous Lambda, which perhaps then it is, we store something in S3 and it is invoked by that item adding to S3, well, if it fails the first time, it will retry up to 2 times and 6 hours. And there is some configuration for this as well. We can set the maximum retry attempts and the maximum event age in seconds. So it is configurable a bit, at least. Stream-based Lambdas instead, the ones that were from DynamoDB or Kinesis, they will store events up to 7 days and up to 10,000 retry attempts. So this is also configurable, maximum retry attempts and maximum record age in seconds. But this is, of course, built in a way to be able to handle a big throughput of events or messages in the stream. Poll-based Lambdas, they will return the message to the queue and up to 1,000 times for retry. And the poll-based Lambdas, as you hopefully remember, is the ones that are invoked based on an SQS queue instead. So if they fail, they return the message to the queue up to 1,000 times. Here's one thing to think about here, by the way, is that what it does is that it's failing the entire batch. When you're having a poll-based invocation, you're able to decide how many messages will the Lambda function poll for each poll. And if one of those messages fail, it will fail the entire batch of messages and push those back to the queue. The SDKs, if you're using those, the different ones that are available, they have different retry counts and retry timeouts depending on which SDK you're using. So it's a good practice to read up on what is the exact behavior for retries for my specific SDK, because these values have changed throughout time as well. But they have automatic retries and they have exponential backoff as well built in the SDKs. But do look up the specifics for each SDK as you're using those. And then beware the retry storm. Retry storm is what happens when you have retries going over and over and over again, which then creates more errors, which create more retries and so on, which will it might push your service, the service that is failing to its limit. And depending on your architecture, that might cause an outage in the end as well. So beware of retry storms. And there are practices for how we can do this as well. And that brings us to the next slide, which is the circuit breaker pattern. And the basic idea behind the circuit breaker is very simple. You wrap a protected function call within a circuit breaker object, and that monitors for failures in a downstream service. And once the number of failures reach a certain threshold, the circuit breaker trips, and all further calls to the circuit breaker return with an error instead, without the protected call being made that means the protected call to the downstream service. So this is what it looks like. Doesn't really matter how the Lambda in this case is invoked, but we build a circuit breaker status check, which we see downstream from the Lambda in this case, and that checks if that third party in this case, or a downstream service, is working as intended, or if there are errors, well, then we store the state, for instance, in DynamoDB, as in this architecture. It can be Elasticache, or it can be more or less any type of service. So when the downstream service fails, the Lambda isn't retrying towards that downstream service. So that's a good way to don't get these retry storms. So that's a circuit breaker pattern. And once the service is up again, we do checks every now and then in the status check. And if the service is up again and responding, well, then we open and are able to push the requests or the traffic to the downstream service once again. Right. Dead letter queues. I've mentioned them a few times already. But really important to use dead letter queues on the services that support those. We're then able to capture events that fail to process. So we can inspect these failed events and messages and then replay them, as I said before. And looking at dead letter queues, we can add these to SNS, Simple Notification Service. We can add dead letter queues to SQS, and we can add them to Lambda. That's the built-in behavior or configuration easily for these three services. And SQS uses SQS as a dead letter queue, which makes sense. And messages from SQS are sent to the dead letter queue if the maximum receives value is exceeded. SNS uses SQS as a dead letter queue. So we attach a dead letter queue to a subscription. And that is important. It's not to the topic that we've created within SNS. So for each subscription, we're able to configure a dead letter queue. And different subscriptions, the way they work, they have different retries as well. So when we use a dead letter queue, it might differ in the way that the dead letter queue is being used. For instance, a message to SQS or Lambda is retried 100,015 times over 23 days. So that's quite a lot. Messages that are going to SMS or text messages, to mobile or to SMTP, email, they are retried 50 times over 6 hours. So that's quite a big difference between those two. And if we're using HTTP endpoints, we can use a custom retry policy. So that's SNS dead letter queues. And Lambda, it can use SQS or SNS as a dead letter queue. So we can either store it within a queue, or we can send it as a message to an SNS topic and then to a subscription of some sort. And Lambda will write the event object invoking the Lambda function after the default retry policy. And that means that we will get the event that invoked the Lambda. For instance, the event data from API Gateway or from S3 if it's an invocation based on S3, for instance. And this is a simple architecture where we have S3 invoking a Lambda function, which then creates a message to an SNS topic to a client. If that message isn't delivered to the client, we can store the message in a dead letter queue, and that message can then be used to replay, either using the same Lambda function if we've built it that way, or we have a separate replay Lambda function, so we're able to deliver that message to the client later on. So that's dead letter queues. Then we have a quite new feature. I suppose this was reInvent 2019 as well, released during reInvent, and it's called Lambda Destinations. And Lambda Destinations is used to capture function failures. So if we have failures within a function, and comparing this with DLQs, we should always favor Lambda destinations over DLQs for Lambda. But an important thing is that Lambda destinations can be used for asynchronous Lambda invocations. So meaning invocations from S3, Event Bridge, and so on. We can not use destinations for synchronous invocations or poll-based or stream-based invocations, only for asynchronous ones. And Lambda destinations, well, we route the execution record, the message that is created based on the execution, based on the result of the function, and that's basically on success or on failure. We can set different destinations. It can be another Lambda function that receives the function result. It can be a queue, it can be an SNS topic, or we can use Event Bridge as a destination as well. And the record contains details about the request and the response in JSON. So that's Lambda destinations. So always use this instead of DLQs when you have your asynchronous Lambdas. Basic architecture for this as well. We have Kinesis invoking a Lambda to store something in S3. If that fails, we can set up on failure Lambda destination to store the message result within an SQS queue. Simple as that. And in this case, well, it looks a lot like a DLQ, but instead we're using the Lambda destinations feature, which is preferred, as I said. Fallbacks, and that's something that is a hot topic because fallback, it is a contingency option, an option that is taken if the preferred choice is unavailable. So think about your primary database is down. We can then have a fallback database, which perhaps is another type of service to be able to maintain a certain reliability within our system. And fallbacks are great, but when we use them often. There was a tweet recently by Mark Brooker. He's an AWS engineer, one of the people making AWS Lambda the awesome service it is. He referenced an article in the Builders Library, the AWS Builders Library, where they talk about why fallback probably isn't something you build into your architecture. And the key point I think he makes is that of latent bugs, because if you build functionality to have fallbacks, you have to use that every now and then or quite often to make sure that it actually works and that it is working with the latest versions of your application. And some of the people that replied to this or had opinions about it were people from Netflix. And Netflix, they use fallbacks a lot. A lot of the things they build use fallbacks in different ways. And they test those by using chaos engineering. So they make sure that the fallbacks are tested regularly. So that's a way to make sure that you don't have these latent bugs in your application. All right, now what? Well, first, perhaps a question. Do we have anyone? Can we configure exponential backoff for retries on Lambda? Well, with the SDKs, we have exponential backoff within the SDK. So that's definitely something that we can use. And I don't have a slide showing how it works today, but looking at the different SDKs is, as I said before, about the retries is definitely something to do, because it differs between the different SDKs how it works. There's one question that I think we'll perhaps take at the end instead. Can lambdas be used for ETL or automation? I am a bit unsure. Can you expand on that question a bit? Show me the demo. Well, we do have some slides left, so no demo yet. All right, let's jump back. Now what? Well, now what? When we have built our application, we use the different practices and patterns and so on. We have, as an industry, we're usually quite good at reactive measures. And reactive measures, I mean, incident response, for instance. Something happens and we respond to that and fix that issue. We're good at disaster recovery. We're good at different testing methods like unit tests, integration tests, and so on. But we want to perhaps verify that our application works instead by using a more proactive approach to that. And the proactive approach that I prefer, that is chaos engineering. So now what? Well, what is chaos engineering? So let's move into that area of this session. So first off, chaos engineering is not about breaking things. When talking about chaos engineering, we often hear the term breaking things on purpose. And it's fine to use that phrase. It's great marketing lingo and it draws attention to the practice. But we have to agree upon that breaking things isn't the purpose. Casey Rosenthal, he was previously at Netflix, where he created chaos engineering along with some other great people. He famously said that, I'm pretty sure I won't have a job very long if I break things on purpose all day. And sure, we do break things now and then with chaos engineering, but the breaking part isn't the purpose. Learning is the purpose with chaos engineering. So it's also important to know that chaos engineering is not only for production. It's often said that we should do chaos engineering in production, but hearing this can be an obstacle for anyone trying to introduce chaos engineering. We, of course, want to do it as close to production as possible, but we can do our experiments in test, in dev, in staging, playground environments, and so on. The more production-like the environment, the better, of course. So we can do it together with replaying traffic, with load testing, and so on, if we can't do it in production yet. And there are a bunch of major companies that are doing chaos engineering without be doing it in production, and they are learning a lot about their environment still. And I mentioned Netflix before, and chaos engineering is not only for big streaming companies. They are used as a reference over and over again because they have brand recognition. They started it all, so they have a head start against everyone else. But you don't have to be Netflix to do chaos engineering. You don't even have to be like Netflix. And when we're talking about serverless, I think that's important to remember as well, because even the smallest startups can have quite big, complex systems fairly quickly. And more companies are using chaos engineering today. And we see that by companies hiring chaos engineers, site reliability engineers, people who do chaos engineering in the companies. So this is kind of the slide you have to have in a chaos engineering presentation. It's from principlechaos.org. It's a website that was released alongside the first book on chaos engineering that Casey Rosenthal and a few others wrote. So chaos engineering is the discipline of experimenting on a system in order to build confidence in the system's capability to withstand turbulent conditions in production. So reading this shows that it's less about doing things that are chaotic and more about experimenting. So the chaos part of chaos engineering is more about what is inherent in our systems. There is chaos in every system. And as I said before, definitely in serverless systems. So let's break that down a bit. So chaos engineering is about performing controlled experiments to inject failure. And once again, experimenting, it makes it sound quite scientific. And to be honest, it is scientific. We create a controlled experiment and we measure the result of that. So some compare it to a vaccine, which these days perhaps is a great comparison, in that we inject failure into the system to make it stronger in the long run. And chaos engineering is about finding the weaknesses in a system and fixing the weaknesses before they break. Because no matter how much we focus on making our systems reliable and resilient to failure, there are always unknown factors that come into play. It can be traffic patterns, third-party dependencies, network issues, deploys, configuration changes, and so on. So by doing these experiments and measuring the result, we can draw out weak points in the system. Finding and fixing these weak points can help us avoid that big outage, the one we know never happened at the right time. And chaos engineering is about building confidence, both in your system and in your organization. So we build, the people, as I said before, are key in building a resilient system. And by doing these experiments, so we learn more about the system, we build confidence, both in how the system works and in how our organization handles these errors. So quickly, a few motivations behind chaos engineering as well, why we want to do chaos experiments. This is a great quote from Charity Majors of Honeycomb, that nines don't matter if users aren't happy. Because most of us, when we build and operate the system, we have dashboards that are full with SLAs and SLOs, SLIs, and whatnot. We measure everything within our system. But it doesn't really matter what the dashboard says unless our users are happy. So what the users are experiencing, that's what we actually want to make sure is working correctly. So a few motivations. Are our customers getting the experience they should from the application or system? Because everyone who builds or runs a system has customers, be it internal or external customers. And if we have downtime or issues, is that costing us money? We know that nothing is free on the internet. So no matter if it's an e-commerce site, an ad-driven blog, and so on, by having downtime, it costs us money in some way, be it in decreased sales or just by users leaving the platform. And what happens when the incident is there? Are you confident that your monitoring and alerting will actually notice that there is an incident? Will your on-call get that page that they need to start engaging with the incident? And You probably have your runbooks or playbooks describing how to act when incidents or outages occur, but is the organization actually ready to handle outages? Hopefully you do your fire drills so that everyone knows how to act in case of fire in your building, but do you do fire drills for incidents within your system? And are you learning from incidents? Every time there is an incident, we have a huge opportunity to learn about the conditions that exist for incident to take place. And using chaos engineering that creates an opportunity to learn without having a real incident in place. And you all know Werner Vogels. I think you all know this quote as well. Everything fails all the time. And Werner definitely knows. Many probably remember the big S3 outage in 2017 and the effect that had on the entire internet. And these types of failures and outages occur all the time. So even if the failure isn't within our system, things can happen that affect us still. If there is an S3 outage, or if, as has happened recently, Verizon has an issue, or Cloudflare doing a code deploy which causes issues within their entire global infrastructure. So we have to be prepared for things that can fail all the time. And this to me is the greatest motivation behind chaos engineering. Once again, we had this slide before, but don't ask what happens if a system fails. Ask what happens when it fails. And chaos engineering helps us reveal what happens when it fails. So let's look at how to run our chaos experiments. And we do it by following some simple steps. First, I'm just going to show you the basic steps, and then we'll look at them a bit more detailed. So first off, we define what's called the steady state of the system. And then we create an hypothesis of what might happen. We then plan an experiment around that hypothesis and run it. We measure and learn from the experiment. And then we scale up or abort and fix if there are issues. So defining the steady state, it's basically the normal behavior of your system over time. It's up and downs. It's up and downs and its highs and its lows. The system, and we find this by using system metrics that might be number of hosts, CPU levels, memory usage, disk space, and so on, or business metrics. Or business metrics might be number of purchases, number of logged in users, searches, and so on. And usually business metrics are more useful. Remember the Charity Majors quote that happy users, that's what we're striving for. And users don't really care what the CPU levels are. They care about being able to add an item to the cart. And remember that steady state isn't necessarily continuous. So the way it looks on a Monday morning might not be the same as it is on a Friday afternoon. So keep your steady state updated as you're doing your experiments. Then moving over to the hypothesis. And a hypothesis is something that we're creating using what ifs. We ask what ifs to try to find a hypothesis to do experiments around. What if my primary database goes down? What if there is an issue with S3? What if Bill isn't in the office today? So we ask these what ifs, and then we try to answer them and create our hypothesis. And remember that chaos or the failure can be injected at any layer of the stack. So it might be at the infrastructure layer by removing services. It can be on an application layer by having errors in the code, or it might be at the human level. As I said, if Bob isn't in the office, he's the one that usually handles these errors. And we use the scientific if-then method. If the primary database goes down, then we will move to the fallback. That's our hypothesis. And when we're doing this, when we're creating the hypothesis, we usually think about things that we haven't thought about before. And in many cases, we find problems, known problems. And if we find a known problem, well, then we fix those before we create an experiment around them. And so if we know that removing the primary database will cause an issue, then there's no point in running an experiment. Then we'll just, we need to fix that issue first. All right, so we have our hypothesis in place. And if the primary database goes down, then we'll move to the fallback. Now we plan and run out that experiment. And planning the experiment, depending on the scale of it, the scale of the system, the scale of the organization, so on. So we gather the people that might need to be involved, and we whiteboard the experiment in detail. And the people that need to be involved, it might be the people who write the code for that specific service. It might be infrastructure engineers. It might be operations people, and so on. And gathering these smart people in a room and talking about an experiment, talking about our hypothesis, that's a great time to learn as well. In many cases, this is the point where we learn quite a lot about our system, how it works. People that don't usually talk about this specific part together get together in a room and talk about it. We talk about containing the blast radius. When we're doing our experiment, we want to create it as small as possible so that the experiment it's not built to create a big outage. So if something goes wrong, if there actually is a failure when doing our experiment, it shouldn't affect the big part of the application, or it shouldn't create an outage. So start small. If we're talking about more traditional infrastructure, perhaps start with one VM, smaller subset of containers, subset of users. Instead of using the global user base, you can start with one country or 5% of users, or whatever the way you have of containing the blast radius is. If we're talking about serverless, it might be using it on one specific function, for instance. It's important that the organization knows what's up. If we want to do chaos experiments successfully, people should know that we're about to do it. So notify the organization and make sure that they are on board with you doing this. And when we plan and run our experiment, we need to have a stop button ready, so we're able to abort the experiment if needed. As soon as we've run our experiment and seen on the metrics, the one we defined earlier with the steady state, that it's working, it's not working, I'll have a stop button ready so you're able to abort. Move that instance back into production again, or abort, cancel the failure injection on those 5% of users. Next step then is to measure and learn from the experiment when we've done it. So we use the metrics we set up before to prove or disprove the hypothesis. For instance, if primary database is down, we will move to the fallback. We'll look at those metrics to see, did it affect the number of purchases, for instance? No, it didn't. It's still on a steady state because we moved to the fallback database and users are still happy, for instance. So we ask ourselves, was the system resilient to the injected failure? That's a simple yes or no question, actually. But a good question is, did anything unexpected happen? When we do our experiments, we usually find things that we hadn't thought about before. This might be both in a positive direction or in a negative direction. We expected this to happen. We expected it to move to the fallback database, but instead it didn't, for instance, or it found a way to restart the primary database and still use that. That's something unexpected. We usually find ways for how the system is more robust than perhaps we knew when doing experiments. And it's important that we share our progress and success when doing our experiments, so people know what we're up to and what happened. Next steps after that are quite easy. We use the learnings that we found to improve our application, our system. We found an issue, well, then we can re-architecture, we can fix bugs in codes and so on. With the confidence that we gained when doing the first experiment, we can scale up. We can use 2 countries. We can have 10% of users or 3 instances. Whatever the way we contain the blast radius before, we can now scale the experiment. And with this increased scope, a bigger experiment, we usually find new effects as well. So, back to serverless then. So let's look at some ways we can use this together. The things we looked at earlier with building, using different patterns, and now using chaos engineering together with that. So when we're creating our experiments, we try to look at some of the common serverless weaknesses we see in architectures. That's a good way to start. So I talked about error handling before, and we use the practices, the patterns I showed before, but no matter if we're using the different releases from AWS, like DLQs or Lambda destinations and so on, doing an experiment around that is a good way to make sure that it's actually working as intended. Sure, we should trust the cloud provider, but making sure, well, I think that's important. Timeout values is an important one in regards to our Lambda functions. What timeout values we set for our functions, they are usually, or in many cases, correct while we are in the steady state. But what happens if there is, for instance, latency within either within the Lambda service or with downstream services and so on? So doing experiments around latency and timeout is a great one. And then we have events. I talked about event-driven architectures, Event Bridge, SNS, and so on. How we handle events is getting more and more important in our applications. So we can create experiments around that. Then we have the thing about fallbacks. If we're using fallbacks, if they actually work as intended, the Netflix example. And failovers. Talking about failovers, it's perhaps around regional failover and multi-region. And having this type of failover isn't only because of regional outages. Those rarely happens. I don't want to jinx us, but they rarely happen. But it might be other things. For instance, if you have customers in other regions and there are issues with an ISP, for instance, it might be valuable to build applications that are multi-regional for that reason. So these are some failures. So let's look at more practical on a few examples. This is a simple web service built serverlessly. The client fetches static data from an S3 bucket. We have an API gateway, and behind that are 2 different Lambda functions. One that is storing or retrieving data from S3, one that is storing or retrieving data from DynamoDB. So we can inject errors into our code to check how we are handling errors. And this is something that we're injecting on a Lambda function, on the actual Lambda function that's running our code. We can remove downstream services. So what happens to our application, the user experience, if we remove S3 from the equation? Will the user still be able to use the application? We can alter the concurrency of functions so that the application isn't able to scale perhaps as intended. And we do that to mimic issues with Lambda, for instance. We can restrict the capacity of tables to once again simulate that there are issues with DynamoDB. Moving on, the same application. We can create security policy errors. As I mentioned early on, since we have both security and configuration on a per function, per service level, it is easy that we introduce security policy errors in our application while deploying and so on. Coarse configuration errors on API gateway is also a simple experiment to do. Different types of service configuration errors, S3, DynamoDB, and so on. And function disk space. Sometimes when we use our Lambda functions, we want to use the disk space, the temp space on that Lambda function. For instance, to cache data or to store data while we are transforming it. And that temp space is limited. So what happens in our application if the disk space is full, if we're not able to use it as intended? And that then brings us to the same application and to perhaps the mother of all serverless chaos experiments, adding latency to functions. And we can do that to simulate cold starts. Cold starts within Lambda is a smaller and smaller problem. It is getting quicker and quicker, and even inside VPCs, we don't have cold start issues in the same way. But still, the difference between a hot start and a cold start is still there, and it might cause issues within our application. We can simulate cloud provider issues, of course. We can simulate runtime or code issues that introduce latency, integration issues, or then, as I mentioned before, to check our timeouts. So that's latency. And this is something that John Cooey, the AWS Serverless Hero fellow of mine, he has written articles on it before. AWS developer advocate Adrian Hornsby has written about it and created a small Python library for it as well. So latency is something that we've used for quite some time now in regards to chaos engineering for serverless. Just quickly, there are some tools out there for doing chaos engineering today. Gremlin is a SaaS solution for chaos engineering. It's mainly for more traditional infrastructure like instances and containers, Kubernetes. But they have one that is for application layer fault injection, Alfie, which can be used together with Lambda. Then there's an open source tool called Chaos Toolkit. And the Chaos Toolkit is, it's open source, and it's built around a sort of plugin system. So you can use it together with more or less any type of technology and some serverless services as well. There is an observability tool called Tundra, and they have added a feature in their tool for introducing failure into your applications to observe how they handle those failures, which is smart to have that integrated into the observability tool. And this is Adrian Hornsby's Chaos Lambda Python library, which you can use with your Python functions. And then we have a Node.js NPM package called Failure Lambda, which I've authored. There's also one for Azure functions and for cloud functions. So these are some tools that can be used for chaos engineering on serverless. All right, so let's look at the failure lambda npm package, which is the one we're going to use in a short demo shortly. So it's npm package for Node.js lambdas. This is the URL, and that text is quite small, but basically it is a wrapper for our lambda functions. So we import it and then we wrap our handler with this failure lambda package. We configure it using parameter store. So the configuration for failure lambda is stored as a parameter, and then we're able to do the configuration there. And that's simple JSON that we're using to enable or disable and to set the different configuration options as well. We'll see those in the demo. We have a few failure modes to choose from. Latency being the first one, of course. So we're able to add that. We can use a status code. So instead of our lambda functions returning a 200 response, for instance, we can return a 404, a 502, and so on to check how does our application handle errors. And we can introduce exceptions in the code, throw an exception. We can fill up disk space in the lambdas, and we can use a deny list to block access to certain services or URLs within our lambdas. For instance, third parties or downstream services. All right, so you already got a sneak peek of this site before when I had to restart PowerPoint. To make it a bit easier to get started using chaos engineering for serverless, I created this site that's basically a demo of it. It's a simple web service that is using a few serverless components that we're able to do the experiment on. This is the architecture that we're going to use. The client fetches static content from an S3 bucket. We have an API gateway. Behind the gateway are 3 different lambda functions. We use 3 to be able to perform more different experiments. They all do the same thing. They all fetch data from DynamoDB and return to the client. And what they return is a URL for an image, which is then fetched from S3. So with that architecture in mind and that application in mind, let's try to create an hypothesis. What if my function takes an extra 400 milliseconds for each invocation? What if my function returns an error code? What if I can't get data from DynamoDB? 3 different what ifs, and also 3 different experiments for us to do. And the hypothesis in this case is that if we inject failure to functions, then my application will use graceful degradation. So users will still get a good enough experience. All right. So moving over to the demo. This is the site. That's big enough. All right, as you can see, function 1, function 2, function 3. They are all being invoked about every 5 seconds. And as I showed in the architecture, what's happening is that the Lambda function is invoked, it's fetching a URL from DynamoDB, and then the client is loading a new image from S3. And it takes about 200, 300 milliseconds for each invocation. So then this is all prepared with that failure Lambda package. And as I mentioned, the configuration is done in parameter store. So we have one parameter for each Lambda function. This is the first one. Let's zoom in a bit more. So this is the JSON. That is the configuration. Right now it's set to false for enabled, so it's not being used right now. The failure mode is set to latency. So for function 1, we're gonna add latency. It's set to a minimum latency of 400 and a maximum latency of 800. So for each invocation where we're injecting this, it's gonna add something between 400 and 800 milliseconds of latency. It's also set to a rate of 1, which means that it will inject failure on every invocation. So let's enable this. True, and save, and move back to the site. And now, looking at function 1 and looking at the invocation time, we can see that instead of, as function 2 and 3, about 200, 300 milliseconds, it is now 800 milliseconds for this invocation, 935 this time, and so on. So we've added between 400 and 800 milliseconds of latency for each call. And this is just a basic example of how this can be used. But in this example, well, it's still working. The client is getting new images. It takes a bit longer, but this can then be used. And we can, of course, add even more latency. We can perhaps use this data to see how would we gracefully degrade this application if it wasn't a good experience for the user. So moving on to function 2. Here we go. Also set to false right now. The failure mode instead is set to status code, and the status code is 404. So that means that instead of an unsuccessful invocation returning a 200 response, it will instead return a 404, not found in this case. And that makes it possible for us to test how our application handles these errors. We've also set the rate to 0.5. And that means that we will inject this failure on about half of the invocations instead of on every invocation. So let's edit this parameter, set it to true, and save. Right. Right now we can see status 404. It didn't load a new image. Next time we get a status 200 and we get a new image. 200 again. 404, no new image. All right, so we can then see that as intended, it's throwing a 404 every now and then, about half of the invocations. But our application isn't really handling the error in any good way. It's just not loading a new image. So that's a way for us to test how our application handles these errors. And perhaps in this case, we should have used some sort of either fallback image, or we could have used some sort of graceful degradation, remove that part from the application after X number of errors, for instance. Then function number 3. And number 3, also set to false right now. It is set to failure mode deny list. And with deny list, we're able to block calls to certain URLs or to hosts. And in this case, the list contains of S3 and DynamoDB. I use a star so that it uses all regions, but this can, of course, be set to specific regions. It could be any type of call that's being made, a third party, if you're using Twilio or Slack or whatever third-party service that is being called. You can then block that to check how your application handles those. The rate is set to 1, so it should block on all calls. Changing that to true. Save. Right, function number 3. There we go. 502 error. Because the Lambda function isn't able to call DynamoDB to fetch a new record with a URL. So instead, the Lambda function throws 502 in this case, because we aren't really handling that error in any proper way. Instead, that error is returned to the client, and the client doesn't really do anything with it. It just displays the error, doesn't change the image, show any fallback image or anything like that. So as I said, that's a good way to test how we handle issues with either AWS services or with third-party services of some sort. Right. And that brings us to the summary slide. There's a lot on the summary slide, but remember that serverless in itself doesn't make your application reliable. The patterns, the practices, the things you do is what makes it reliable. And there are, well, this is a summary of a lot of the slides we had before. Decoupling architectures, let AWS handle errors and retries, for instance, use Lambda destinations. And if you're using fallbacks, make sure to test them so that they're always up to date and working with your code. And chaos engineering, well, it makes us find weaknesses and fix them before they create outages instead. If you want any more, here's a slide with a few different links you can use. We can probably post this afterwards so you get the links there. To, for instance, Yang Kui's great slide or deck on different patterns and practices. Jeremy Daly's website that shows some patterns as well. The Amazon Builders Library, a blog post once again by Yang Kui around timeouts, retries, and backoffs, and then the link to that serverless chaos demo app. And that's the thank you slide. So I suppose back to any questions.
Okay, Gunnar, hi. Wow.
1 minute to spare.
Oh my God, that was a great presentation, spectacular, Gunnar. Actually, there is a lot of questions. Thanks, you just answered a few ones, but yeah, that demo exceeded my expectations that I was wondering about chaos engineering. So it was very great. I hope everyone here in Peru just feel excited as much as I feel right now. So I feel very good about viewing this kind of chaos engineering applying in real scenarios. So I can imagine if I can just test this kind of stuff in hundreds of Azure functions or Lambda functions. Yeah, really great to have this scenario. So let's go to the questions. Let's see if I can read this. Okay. About we're talking about a little bit about application load balancer in front of Lambda. So what is the actual need? I don't know if it's related to chaos engineering, but I think goes a few steps after about where's the really need of put Lambda functions behind application load balancer. If it's necessary sometimes to do it, it brings more reliability or robustness or resilience, or what can we do with this?
Well, I perhaps wouldn't say that it brings more reliability, since ALBs are instance-based. They do scale. They are you rarely have problems with load balancers that way. But there are certainly use cases when you might want to use ALBs. There are some certain things that API gateway perhaps can't do that you instead need to do using application load balancer. Trying to think of an example right now, but it's after midnight in Sweden, I guess. I'm a bit stuck, but so sorry about that.
But actually, I don't see any production. I mean, application load balancer behind Lambda functions in production, but I think I don't know. Same as you, can't think exactly scenarios about that, but it's homework. Okay, let's.
Yeah, it might be it might be for instance when you're working with sessions, for instance, since most serverless things and things you're doing with Lambda are stateless. You don't have any sessions in that way, but going through an application load balancer instead, you can retain sessions in a different way, and then you of course need to handle the sessions somehow using DynamoDB, for instance, or something like that.
Yes, thanks. Okay, let's go to the next question. What are the common problems of a serverless solution and its possible solutions? I think it's related to what actually you just said about the common problems of the service applications are latency, or I don't know whatever kinds of problem, but you mentioned that latency is one of the most common problems that affect serverless solutions. But can you tell us about what other kind of problems? Maybe just one thing you mentioned is the connection for DynamoDB maybe is rejected. Another kind of stuff, actually, what happens about the queues also. So please.
Yeah. Probably I'd say that the biggest issues that you might run into is that if you're not using the perhaps best practices and so on while building applications, if you're using the way you've previously built applications and moving that to serverless, you might run into different issues. Because the way we build applications serverless is a bit different. So a lot of the services are really robust. They work very well most of the time. There are rarely issues, but when there are issues, since we rely so much on the services being there, it's quite common that people don't have the correct error handling and so on. So I think that was a bit what I touched about before as well. What are common issues otherwise? Well, a common issue that I see is that we're trying to sometimes fit the wrong things into serverless, and perhaps long-running processes, things that run for a longer amount of time into serverless or into Lambdas, when instead perhaps they should be run in containers, using, for instance, Fargates. At least it's serverless-ish.
Yes, of course. Okay. Thank you, Gunnar. Let's go to the next question. I want to put you on the screen. It's a mix of two questions. Could you share an example of step functions? But instead of that, because we are in the final part, just a question and answer thing. What about the step functions? You didn't tell us. Maybe in your examples, we see a lot of Lambda architecture with different kind of serverless services in AWS. But what about step functions? Can we run the same scenario with these libraries that you just show us with the step functions too?
Well, step functions perhaps needs an entire session on its own. So, but in short, talking about step functions, we usually talk about orchestration. That we do it to it's state machines, so we do orchestration or kind of workflows. But one thing with step functions is that it can get quite expensive to use step functions if we're using it incorrectly. It can easily become quite expensive to use it. So we often have to choose between either orchestration through step functions or perhaps the more event-driven architecture using other serverless services. So once again, the answer is, I guess, it depends on the use case, what you're gonna do. I know that my friend Jan actually wrote a great blog post on this just the other day, with orchestration versus event-driven architecture. I can probably find that and post the link in the comments as well.
Okay, great.
But yeah, step functions is definitely good for certain use cases, but beware of the cost of using step functions.
Okay. Thank you, Gunnar. Okay, next question about decoupling architectures is, are these serverless components of the decoupling architecture similar or the same as the microservice architecture? I think you talked about a little bit a few minutes ago about that microservice architecture is actually very similar to the serverless architecture in AWS, just with the few considerations of we are decoupling a lot more.
Yes, it is a lot similar to microservices, but in many cases we are decoupling even more. Yes, so a serverless service might be even smaller than a microservice in some cases. But a lot of the rules that apply to microservices and perhaps best practices around that, many of those apply to serverless services as well. And the word or the naming microservices is definitely used a lot by people in serverless as well. Yeah.
And the other question that I just put on the screen about it is better or how we can achieve just testing or chaos engineering, but using all the features that Lambda has about test environments, different stages in API gateway, in Lambda function, and if this chaos engineering exclude the security part of testing lambdas, or is just or we're checking just it's another topic separately of this chaos engineering process?
Well, in regard to chaos engineering, you can definitely use it for security as well. There is this specialty field within chaos engineering that's called security chaos engineering, which focuses entirely on the security part of it. So think about the way you perhaps do some security testing today, but that's usually also a more reactive response to security. But using chaos engineering experiments built specifically for security, and they are, once again, a more proactive approach, the same as we did with testing how certain things fail. But we can use that for security as well. Yeah, nice. So definitely use that together with security.
Okay, thank you. I just posted the Yankee post that you tell me.
Yeah.
The choreography versus orchestration. So everybody to read about this.
Yeah, it's a great post.
Okay, let's see another question. I have a lot of questions. I have to just choose. There's a good one. Just to summary what you have been talking about these 2 hours here is what are the key services for everyone who just want to achieve reliability in their architectures? So in terms of AWS services, what services we have to look for?
Wow, that's well, I'd say that the serverless services, or all the services that are within the serverless landscape, they are built with reliability in mind. So as I mentioned early on, they have these features for elasticity so that they're able to scale. They have high availability, that they are multi AC, for instance, and they are robust in that if there are issues, it automatically tries to solve those issues. So the key services for reliability in serverless, well, I'd say that the services that I mentioned early on with for instance, using SNS, SQS, and Event Bridge for decoupling and so on, those are key services in regards to the reliability part. And looking at the other services like Lambda, API Gateway, and so on, there I'd say it's perhaps a more a factor of using the options that are built into the services, using, for instance, DLQs, using Lambda destinations, and so on. By using those, we're able to achieve a higher reliability. So,
okay,
yeah.
Well, and what about we have this kind of architecture with different services, Lambda, CQS, with DLQs, with FIFO queues, I don't know, what kind of all complex stuff in our architectures. We have to achieve observability to maybe CloudWatch. CloudWatch is very useful here. I don't know. You didn't mention anything about CloudWatch. Sorry if you did and I missed that. But what about CloudWatch? Is core service here about reliability or not?
Well, observability is definitely needed to be able to build reliable applications in some sort. There are, of course, the AWS options with CloudWatch and X-Ray, for instance, for tracing, using those to be able to observe what happens in your applications. That's really important. And there are also a lot of third-party options there that perhaps pushes the envelope even further in regards to observability. They are all a bit different from each other, but I mentioned Tundra before, Epsagon, Lumigo, Dashbird, probably missed a few, but Datadog, New Relic, and so on. They are all great tools for observability.
Thank you. And we have last questions about the question that we have to make to our audience. And maybe you can choose one questions, because there's a lot of people just commenting and asking great questions, and I will give all of them AWS credits. And also I want you to make a question for everyone. Hope everyone's there to just to answer correctly. So you tell us if it's correct or not. And but before that last question that you have to do, let's go with this one, but that you read, but you said that it's for the final minutes.
Oh, yeah.
So yes. Says this. Joskar asks us about how you see the future of serverless services maybe operating a multi-cloud schema.
Yes. If I understand the question right, well, one thing about serverless is that and that's quite often talked about, the lock-in of serverless, that the services in AWS are so different from the services in Azure or Google Cloud that you're kind of locked to that cloud provider. So if you want to go multi-cloud with serverless, you definitely have to build 3 completely different versions of your application. I guess a lot of people say that it's easier using, for instance, Kubernetes or something like that to move between the different cloud providers, but I don't think you can compare it that way either. Because the offerings from AWS in regards to serverless is a lot broader offering than is available in Azure or Google Cloud at the moment. So you can't really build in the same fashion in the different cloud providers. So for them to be multi-cloud in the sense that you should be able to move between them as well, then I guess Azure and Google Cloud need to step up their game and deliver better and more services in a serverless way.
Okay, great. Thank you. So please, could you ask a question open to all our audience? Let's say, or I don't know, maybe let's go with two credits of $25 each. So for one question, the first one who asks is the first one to win.
So I should ask a question.
Yes, of course.
All right. No, sorry. That's a tough one. All right. So an easy one, but
okay, let's go.
Yeah. Should we prefer to use DLQs or Lambda destinations for our Lambdas, asynchronous Lambdas?
Okay, I'm going to say it in Spanish for everyone. Ahí la pregunta que lanzó Gunnar fue si es que para operaciones asíncronas tenemos que usar Lambda destinations o SQS dead letter queues. Esa es la pregunta. Ahí está, tenemos la primera persona que ha respondido. We have the first person just asked the question, Gabriel Co12 Lambda destination. Y Ángel ISS SQS. So.
And the answer was Lambda destination.
Lambda destination. So Gabriel Co12, you're the winner. So that was easy. That was an easy one. It's not fair. Let's go with another question. Maybe more to 200 level.
A tougher one.
Yeah.
Wow. Let's see. What have I talked about? A tougher question. It puts me on the spot. I should have prepared this question.
Yes, spontaneity is more. Yeah.
Sorry. What do you say, Carlos?
No, being spontaneity is better.
Yeah, it's hard after midnight, though. But okay. Tougher question. All right, this one isn't a technical question, but it's something that I mentioned in the presentation. Who was the creator of chaos engineering?
¿Quién fue el creador de la ingeniería del caos? Hay algunos que hayan estado revisando la web de chaosengineering.org, así que, pues, we have to.
Yeah, okay. A person then. To make it a bit harder.
The person. Claro, la persona, no la empresa. maybe I expected you to talk about a little bit about the Seaman Army of Netflix, but it's like, what do you think about you? In the meantime, but what about the Seaman Army and Netflix?
Well, the tools that Netflix created early on with the Chaos Monkey and Simian Army and so on, really great tools, but they are built. They are definitely not built for serverless. They are built for the type of infrastructure that Netflix used at the time, which was mainly EC2. So Chaos Monkey, which randomly shut down EC2 instances for them in their infrastructure to make sure that there are some names, but not the name, not the right name, the name I mentioned yet. But keep googling. So it shut down EC2 instances at random to make sure that their application was robust enough to handle that instances were removed, and then they created some other monkeys as well to be able to add latency to do other stuff in their environment. So yeah, really great tools, and they have definitely been used by other companies as well afterwards, and inspiration for a lot of the tools that are out there today.
Of course. Great. So talking about the question, Gunnar, we have to just lose those credits because no one has the right answer. Okay. What about the two names? It's actually people who maybe share with the actual owner of the chaos engineering, Greg Orsel or Laurie Hochstein. Have to be some.
Oh yeah, definitely. Both are from Netflix and were involved, but the one I mentioned and the one that perhaps is accredited for creating
it's not you.
No, it's Casey Rosenthal.
Casey.
Yeah. Wow. Right.
Well. We have to Google a little more harder, but that was great. That was great presentation, Gunnar. I really appreciate that you come with that level of expertise to share with us. I really loved about the demo side that you mentioned and that you show us. That's something great to just view how the chaos engineering is showing us the results and view the performance of the application actually degraded or get better between those kind of scenarios that you just mentioned. So that was really great, and hope you can come back with another great talk. I don't know, the next month or maybe upcoming weeks. I don't know, but it's gonna be great just to be some kind of war between Azure, because I just saw that you also perform Azure chaos engineer. So it would be great to have just like who has the better performance in the exact scenarios between those platforms. So it will be great.
I can answer that straight away. And it's not Azure. No, but you're right. I actually did a presentation, my first Azure presentation the other day, which was fun. And to do that, I had to build the same demo using Azure services, and it was tough. Cold starts is definitely an issue in Azure. Let me tell you that. But I do have a new presentation coming up, which I will be presenting at a few conferences shortly. That is. Let's call it the next level after this, which is how to do things perhaps a bit more automated and have it as part of your deployment pipelines. So I'd be happy to come and present around that as well.
Of course. We're really love to see that upcoming weeks. We have to keep talking these weeks until you have this presentation. We just check around about how we can do it in the upcoming meetups. Okay, so great.
Mm-hmm.
Thank you again, Gunnar. And just you have to go to sleep right now because it's midnight, or I know right there. So thank you again, and I'm really happy to just come here and show us what you show us. It's really awesome, and hopefully we can chat together again in the coming weeks.
Of course. Yeah, thanks for having me once again, and thanks for everyone watching and asking questions and commenting. It was great.
Well, thanks. So, well, I'm going to switch Spanish right now.
One last thing first.
Okay, just please.
Please, if you have any more questions after this, do contact me on Twitter. My handle is on the screen right now, or connect using LinkedIn. I try to answer everything I can, or at least point you in the right direction if I can't answer. So yeah, do connect.
Okay.
Now I'm done.
Thank you, Gunnar. Thank you, Gunnar. Good night. Muchas gracias, muchachos, a todos por haber venido, por estar y por quedarse estas 2 horas, casi 2 horas y media. Ha sido espectacular tenerlos aquí. Y les voy a mostrar solamente algunas cosas en las que nos podemos involucrar las próximas semanas. Que justamente va a ser de valor para ustedes. ¿Sí? Déjame un segundo que aquí lo coloco bien. Y pues eso es lo que nosotros venimos realizando durante el mes de agosto, y hoy día 15 hemos tenido la oportunidad de tener aquí a Gunnar. El 22 es el AWS Online Community Day, la TAM, donde vamos a estar todos los líderes de Latinoamérica aportando nuestro granito de arena para seguir evangelizando cloud computing y en AWS, obviamente. Y luego, ya para terminar agosto, tenemos 2 grandes charlas. Va a venir Andrew Brown de Canadá, es un AWS Machine Learning Hero, y hablaremos sobre cómo llegar de manera rápida nuestro fast track hacia SageMaker Autopilot para hacer algo de Auto Machine Learning, que es uno de los temas que también voy a tocar en el día 22, que vamos a estar dando una charla con Gerardo Castro y vamos a hablar sobre Autopilot también. Solamente que Andrew Brown viene a hablar sobre algo mucho más general y mucho más profundo acerca de Autopilot. Y el día 29 también vamos a tener detección de intrusos en tiempo real, ¿sí? Con un invitado aquí de Perú, que es pues me acabo de acá, es Luis Grados. Sí, Luis Grados nos va a hablar sobre detección de intrusos en tiempo real, y va a ser una demo espectacular, así que no se la pueden perder. Y adicionalmente tenemos una charla acerca de el LAMP Stack en Serverless. El LAMP Stack en Serverless, que lo va a dar Claudia de Kaleidos. Así que estén atentos en cómo vamos a terminar este mes de agosto, y ya estamos preparando el mes de septiembre para ustedes y llenarlos de información sumamente valiosa. ¿Okay? Gracias a todos y ya nos vemos pronto. Thank you, Gunnar, again. Let's go sleep. And I'm going to have lunch right now. So have a great day and see you later. Bye bye. Ciao, ciao a todos.